Determine where f of x equals quantity x squared minus 10 times e to the x is concave up or concave down, and find the points of inflection. If we graph f of x equals x squared minus 10 times e to the x, we might be able to find approximate points of inflection by looking at the graph. So let's see, when we see where does this go from being concave up to concave down? It is kind of hard to tell, and I can see a definite place where it's concave up through here. Let me instead do a graph of f double prime of x. So if I do a graph of f double prime of x, I can see that the f double prime of x crosses in two places. F double prime of x crosses at approximately x equals negative 5.64 and at approximately x equals 1.464. So these from the graph of f double prime of x are where I would suspect my inflection points are. Now, there are two problems with this. The first is from this graph, I don't know for sure that these are the only two places that this f double prime of x crosses. And the second is that these are approximate values. I might need exact values. I'm curious if I type that into WebWork whether or not that's a high enough degree of accuracy. Negative 5.464, comma 1.464. You check answers, and it tells me that's correct. So for this problem, using the graph was good enough to give WebWork what it wanted. Another option, if I wanted to use the computer, would be to ask Wolfram Alpha just what are the inflection points. Somehow, I agree that neither one of those is really as fulfilling as we might want. So Wolfram Alpha again gives me these approximate locations, but I would like to find these exact locations. So let's see how we would do that. The important thing to remember here is that concave up or concave down is determined by the sign of f double prime of x, and that points of inflection are places where f double prime of x changes sign. So to find the second derivative, I first have to find the first derivative, f prime of x. I'll need to use product rule. 2x times e to the x plus x squared minus 10 times e to the x for my first derivative. Now this is a place where it helps a lot to use algebra to rewrite my original f prime by factoring e to the x to give f prime of x is equal to e to the x times 2x plus x squared minus 10. And then it's common to rewrite this so that the x squared term is first. So I would rewrite this as f prime is equal to e to the x times x squared plus 2x minus, this is my first derivative, and now I go to take the second derivative, and again I need product rule. E to the x is a, and x squared plus 2x minus 10 is b. So f double prime of x will be a prime b plus a prime, so e to the x times x squared plus 2x minus 10 plus e to the x times 2x plus 2. Now again, it's helpful to me to factor out the e to the x, and I have x squared plus 2x minus 10 plus 2x plus 2, and I can combine some like terms here. I could simplify my f double prime of x here to be e to the x times x squared plus 4x minus 8. I'm going to try to go through my sign chart process here. My first step is to solve e to the x times x squared plus 4x minus 8 is equal to 0. So this could be either e to the x equals 0 or x squared plus 4x minus 8 is equal to 0. If I try to solve e to the x is equal to 0, this has no solution. The graph of y equals e to the x never crosses the x-axis. So e to the x is never equal to 0. Turn our attention to x squared plus 4x minus 8 is equal to 0. This is one we actually can solve. We might hope it factors. Sadly, it doesn't. So in order to solve it, we'll need to either use completing the square or the quadratic formula. Remember the quadratic formula, when we're trying to solve an equation of the form ax squared plus bx plus c equals 0, the solutions have the form x equal to opposite of b, plus or minus square root of b squared minus 4ac, b squared minus 4ac all over 2a, all over 2a. And if we play the pattern matching game here, we say we're trying to solve 1 times x squared plus 4x minus 8. So for our particular instance, our values are a equals 1, b equals 4, and c equals -8. So if we plug that into the quadratic formula pattern, we will get x equals opposite of 4 plus or minus the square root of 4 squared minus 4 times 1 times -8 all over 2 times 1. Since I'm doing this problem by hand, I'm going to start breaking things down a bit more. This is -4 plus or minus 16 plus 32 all over 2. So this is opposite of 4 plus or minus the square root of 48 all over 2. The square root of 48 takes a little bit of thought here. I can take this to be 16 times 3. So this is equal to the opposite of 4 plus or minus the square root of 16 times 3 all over 2. And then when I go to clean this up, square root of 16 times 3 is equal to the square root of 16 times the square root of 3, which is 4 times the square root of 3. So when I go to clean up this, x equals -4 plus or minus square root of 16 times the square root of 3 all over 2. I can clean that up as -4 plus or minus 4 times the square root of 3 all over 2. And then I can divide everything through by 2 here, and I get x equals -2 plus or minus 2 square root of 3. So this actually gives me two solutions. This gives me x equals -2 plus 2 square root of 3, and x equals -2 minus 2 square root of 3. So I have two solutions, and I think that these are the values of the inflection points that the graph gave me a minute ago. Let's go back and confirm. So the first solution that I thought I saw, so this first inflection point that I saw where f double prime of x was changing sign, looks like it was about x equals -5.464. When I solved f double prime of x equal to 0, I got x equals -2 plus 2 square root of 3. So let me type in -2 plus 2 square root of 3. Oh, that's the larger one. I actually want here the -2 minus 2 square root of 3. And you see that this is not exactly the same answer, but it lines up to 3 decimal places. And then if I look at the other place where I saw f double prime of x equaling 0, that happened at x equals 1.464. And if I put in -2 plus 2 square root of 3, I get that, I see that also right here, this 1.464. So I can, with algebraically, determine the exact location of the inflection points. I see f double prime of x being positive, starting at -infinity, all the way up to this -5.464, or the exact value is this -2 minus 2 square roots of 3. So the first interval where f of x is concave up is -infinity to -2 minus 2 square roots of 3. And then as f double prime of x starts being positive again, after this 2 plus 2 square roots of 3, positive infinity business. So these two intervals together, their union, these would be the places, these would be the intervals where the original f of x was concave up. And let's confirm that by typing it in. So the leftmost interval is -infinity to -2 minus 2 times the square root of 3. And on this interval, f is concave up. Middle interval is -2 minus 2 times square root of 3 to -2 plus 2 times square root of 3. And on this interval, f is concave down. And finally, I have -2 plus 2 times 2 square root of 3 and positive infinity. And on this interval, f is concave up. Now, what I'm curious about is whether WebWork took the approximate answers for these intervals as well, because that is just interesting to me to think about. So did WebWork take the -5.464? If I change that and change this to 1.464, will WebWork also accept that as being correct? Yes, it did. So both the exact and approximate answers work in terms of getting WebWork to give you the credit for the question. And the big conceptual thing you have to do is recognize that you can figure this out by looking at f double prime of x. F double prime of x controls the concavity of f of x.